We were live on Facebook, but I wasn't recording this. All right.
Oh, I see.
We lost a little bit. That's okay. Not the important part, which is, of course, Justin's talk. So in March, we'll have an open house, which is a concert. That'll be a cello piano duo that Jason Solomon in the music department has lined up, which is sure to be a lot of fun. I've listened to some of their pieces. Beautiful, beautiful music. They'll be doing a mixture of some pre-recorded and some live pieces, I believe, for that open house. Then in April, Professor Amy Lovell is going to be giving our talk. And in May, I'll be giving the talk. So Amy and I will be closing out the year this year with, and I don't even know that we've determined what we're talking about yet. We'll have to put our heads together and figure that out. It's, you know, if any of you are teachers, you know how the last year-ish has felt, right? It's kind of pulling things together as fast as we can. So, but I'll at least say that I'm sure Amy's talk will be fantastic because she always gives a great talk. All right, so let's go ahead and get started. I'm just going to give a brief introduction for our speaker, Justin Robinson. Justin is a graduate student who's going to be finishing up in the next couple of years at Georgia State University, getting his PhD in astrophysics. And he studied undergrad at St. Mary's, which is out in California. Sort of east of San Francisco. And we talked a little bit about that because I went to high school out in the Bay Area. And I think you said you lived in Redwood City for a while. So you're a lot younger than me, but we were sort of in the same part of the world at another time. So that was fun to find out. And I believe you said, is that right? You were the only physics major the year you graduated?
The only astrophysics, yeah.
Only astrophysics major, a small school, right? Well, from one small school to another, we are very proud of you for having attended a small liberal arts college. We think that gave you the excellent education that brought you to Georgia State. Justin is now studying for his PhD at Georgia State, and we're going to hear about some of his research work tonight. And with that, I will turn it over to Justin. Thanks so much for being here tonight.
Thanks so much. Thanks for having me. Let me go ahead and share my screen. It's worked up until this point. There we go. And a quick thumbs up. Can people see what I am showing right now? Perfect, perfect, perfect. Okay. Thank you so much, Chris. It was a really lovely introduction. Thanks so much. My name is Justin, and I get to study some pretty cool stuff. And I want to talk about that stuff with you, and I want to show you some of the things that I do. I look at galaxies. I look at what they're made of. I look at how they behave. And I look at their supermassive black holes that are nestled down there in the center. So just to set up, I want to talk about something that you've probably heard once in your life at least, and that is that the universe is expanding. Now it doesn't, whoops, there we go. Now it doesn't quite look like this because this is a GIF that I found on the internet, but I think that it does a good job into getting us in this headspace where if we were able to take a universe-sized clock and crank it up to 11, this is kind of what it would look like, because what we observe is that the vast majority of galaxies in the universe are speeding away from us. And the farther that a galaxy is away from us, the faster that it's running away. And that's kind of how we figured out how the universe was expanding in the first place, because we see this no matter where we look in the sky. We don't quite know why the universe is expanding, but we know that it is. The universe is densely populated with these galaxies. It's estimated that there are about 2 trillion galaxies in the observable universe. So the big picture that I want to focus on today is how we actually understand the behavior of the universe as a whole. What is it doing? How does it behave? What is it made of? And so that gets me thinking, if we want to understand the universe, then I would probably want to look at the stuff that makes it up in the first place. So I want to look at each of these things and I want to really understand a galaxy and what makes it up and how it behaves. So let's go ahead and do that. Let's break down the anatomy of a galaxy. This is an image of Andromeda, which is the nearest major galaxy to us. Andromeda is a spiral galaxy, and galaxies are just large collections of stars. And in spiral galaxies, it's a large collection of dust, gas, and stars. And spiral galaxies are a specific subset, but we're going to look at that right now because they're my favorite. And they're the types of galaxies that I'm going to keep talking about specifically throughout tonight. So if you have a spiral galaxy, the first thing that you got is a disk. Spiral galaxies are big, fluffy space pancakes. And in that pancake, you have all of the spiral arms of the galaxy and the majority of gas and dust that make up your galaxy. The next thing that you got is a central spherical bulge that houses millions of old red stars that are all orbiting the center of the galaxy in roughly circular orbits. So if you've got millions of stars that are orbiting in circular patterns in a bunch of random orientations, the thing that you're going to make is a sphere, a spherical shape. So you've got your big space pancake, and then you've got the sphere, the bulge in the center. Very far down at closer scales, you have the nuclear region, and all of the stars in the bulge are rotating around that nucleus. And then nestled in that nucleus, you have a central supermassive black hole. Obviously, the stuff down there in the center isn't to scale, but to give you a sense of scale, a supermassive black hole can be anywhere from the size of maybe roughly the orbit of Mercury to the size of an entire solar system. And then the size scale of the supermassive black hole relative to the bulge is pretty much like comparing the size of a fly to a football stadium. And then to go from the bulge out to the disk is about 10 times that of the bulge. So 10 times the size of a stadium to get to the size of the disk. The thing with this image, though, is that it's taken by a telescope that's designed to detect the same energies that our eyes can detect. But we know that photons, particles of light, can exist at energies that are either too energetic for us to see or too small energetic for us to see. Photons can have a very large range of energies, and that's what this image is showing here. This is an image of a galaxy in multiple energy regimes. It's a very famous spiral galaxy. This is the Whirlpool galaxy. The photons, the energies that we can detect with these things, we call that the optical, because when we name things in astronomy, we're very clever. If we were able to somehow shift the energies that we can see with our eyes down to slightly lower energies, then we hit the infrared, heat. They are very good at tracing heat. And so if you pay attention, the optical and the infrared images don't really look that different. And that's because the infrared is very good at tracing out these star-forming regions, where you're taking a bunch of gas and dust and you're compressing it down. When you compress a gas, you increase the pressure. And when you increase the pressure, you increase the temperature. And so when you look in the infrared, it will tell you where all of the stars you are creating are. And the star-making factories in a spiral galaxy are in the spiral arms. That's where all your gas and dust is. So the infrared will tell you where the spiral arms are, because that's where all the stars are being formed. If we can shift again to even lower energies, we get into the radio. And the radio traces out really, really cold stuff, really cold molecules like carbon dioxide, and really cold just atoms in general. So it actually, for a spiral galaxy, traces out all of the hydrogen in your galaxy. If we shift to stuff that's too high of energies for us to detect, we get into the ultraviolets. And this is what's tracing out the biggest, most energetic stars. And you can kind of see that there's a lot less structure in the UV image than in the optical, in the infrared, or even in the radio. And that's because to create big, massive stars like that, you need a lot of resources, which means they're harder to make, which means they're more rare. So when you look in the UV, and all it's showing you are those big, massive, highly energetic stars, it's going to show you where the galaxy was able to make those. And it's not in as many places as it can make the colder, smaller stars like it can in the IR. And then finally shift to the highest energies, and that puts us into the X-rays. And this will show you the most energetic gas, the gas that's moving at the fastest velocities that are the highest temperatures, millions of degrees. Now, even if we were able to see all of these energies simultaneously, it still would barely scratch the surface in terms of the total amount of stuff that makes up the universe. And that's because we're pretty sure of what the breakdown of the universe is. 70% of the universe is hogged up by this thing called dark energy. Now you might be asking yourself, or maybe you have in the past when you've heard this, what is dark energy? And if you know what dark energy is, send me a message and then I'll shoot you back a picture of me with my Nobel Prize. 30% of that pie is the total amount of matter in the universe. But the problem is 80% of that slice of the pie is this thing called dark matter. And again, you might ask yourself, what is dark matter? And again, the answer is Nobel Prize. But this stuff is slightly easier to study and to understand. And then just 20% of that slice is finally normal matter, the stuff that we interact with every day, the stuff that will emit photons at any of the energy regimes that we can detect. And so you've got your stars, your gas, your dust, your galaxies, all the stuff that we know that we interact with every day. So at the end of the day, the stuff that we interact with is 5% of the total amount of stuff that makes up the universe. 5% of the pie to study the rest of the pie. So that's the breakdown of the universe. Let's start zooming in. Let's zoom in on the kind of the idea that we have that we agree with on how galaxies work. So in terms of a galaxy, you have the bulge and you have the disk, the stuff that's normal matter, the stuff that we can directly detect. And then we're pretty sure that each galaxy is surrounded by this bigger, more massive dark matter halo. And the reason why we think that is because we're pretty sure that we know how gravity works. So we know that when you have mass, you will create gravity. And when you have more mass, you will create more gravity. And if you're closer to something with mass, you're going to feel more of that gravitational pull. So in terms of things that are moving, things that are orbiting around something, think of the solar system. Now, obviously none of this is to scale, but the speeds of the orbits are to scale. So we know that Mercury, for example, orbits faster than Neptune because Mercury is closer to the sun. It's closer to the source of gravity in the solar system. And we know that if somehow we increase the mass of the sun, then all of the planets of the solar system would orbit faster because there would be more of a gravitational pull, more things that are making them move faster around the sun. So looking back at a galaxy, you might think, well, it looks like there's the most mass concentrated at the center, and then it's less concentrated the more that you get out to the outer edges of that galactic disk. So you might think that the things would orbit the fastest at the center, and then that orbital speed would kind of decrease as you step outwards. That's a fantastic hypothesis, only it's the opposite of what we observe. What we observe is that things move very, very fast near the centers of galaxies. But even if you approach the edges of the galaxy, the parts that we can detect, the speeds at which things are moving don't slow down. The speeds of the stuff at the outer edges of the galaxy are moving at almost the same speeds as the stuff at the center. The only way that that could be true is that this galaxy is surrounded by a lot of mass, things that are keeping up the force of gravity, keeping up the speed that these things are moving at. And this very large halo of extra mass can't interact with normal matter, and it can't emit light. So what do you think we got together and called the thing that doesn't interact and doesn't emit light? We called that dark matter, because again, you're going to notice that we're very clever. There is a rogue theory out there that not many people prescribe to, but the theory basically says that instead of relying on dark matter to make these things happen, let's just tweak the law of gravity just a little bit to explain what's happening at the outer edges. And I only mention that because I like to call that the I tried so hard and got so far, but in the end, it wasn't even matter theory. But the vast majority of astronomers, cosmologists, observational astronomers like myself, all prescribe to this theory that there are dark matter halos that surround each galaxy because it does the best of explaining the behavior of the universe as a whole. So we've gone from the outer universe, we've gone to the breakdown of the galaxy. Let's keep on zooming in and see what we can find out about those supermassive black holes that are at the centers of every galaxy. Well, what's the closest supermassive black hole to us? That would be the one that's sitting at the center of our Milky Way galaxy. That's Sagittarius A star. And what we tried to do, the only way that you can study a black hole, because black holes don't emit light, so we can't study them directly, but what we can do is study the effect that they have on the material around them. So this group at UCLA, for over 25 years, tracked the motions of individual stars around this dark central point. So each of these little circles are individual stars in the central bulge of our galaxy. And they traced their orbits over a period of 25 years. And they took the speed at which they're moving and the orbital information themselves of all of those individual stars, and were able to measure the fact that that central point, in order to make the stars do what they're doing, has a mass of about 4 million times the mass of the sun, packed into a size that's about the size of Mercury's orbit. The only thing that can be that massive, packed into a relatively small space, is a supermassive black hole. And this discovery, this science was so revolutionary that it actually won the Nobel Prize in Physics last year, where Andrea Ghez was the main leader of that research, of the team that studied the center of our galaxy for 25 years and were able to get precise details, not only of direct evidence that there is a supermassive black hole at the center of our galaxy, but its mass and a bunch of other properties of that black hole. Now, when you think of a black hole, you might think of vacuums of the universe, right? Things that are sucking in everything and it's feeding on its environment around it. The cool part, though, is that our black hole, Sagittarius A star, isn't really feeding on anything. Sometimes things fall in, but most of the time, things are just orbiting around it. It's not sucking anything in. So I want to switch then. I don't want to look at those black holes. What I want to look at are black holes that fit the description that you always think of, things that are actively feeding and snacking on their environments. And what we call the galaxies that host those are active galactic nucleus, or AGN, host galaxies. And even if you've never heard that term, I bet that you've probably seen an image or a depiction of what these things are. So for example, if you see an image like this, it's a very famous image that's used of a black hole. This is an actively feeding black hole. Or if you've seen something like this, or if you watched the movie Interstellar, because the black hole in Interstellar, Gargantua, is technically an actively feeding black hole because it's got a disk of material around it. It's orbiting the black hole. Some of the stuff is falling in, being eaten, but we call that as being accreted. So we call that disk, that structure, an accretion disk. But each one of these, even the one in Interstellar, which is actually the most accurate depiction of a black hole we have in media, each one of these is fake. So what I want to do is get a more realistic representation of what the environment around a black hole that is actively feeding on its environment looks like. So here is a real AGN host galaxy. This is NGC 4593, NGC standing for New General Catalog, 4593 meaning that this was the 4,593rd galaxy that we put in this catalog. If I were able to zoom in somehow all the way to the center, meaning, remember, my spherical bulge is the size of a football stadium, and then the disk is about 10 times that size. So I'm going from something that's 10 times the size of a football stadium down to about the size of a baseball. So if I were able to zoom in that far, the thing that I would see would probably be something that looks like this. And again, this is an artistic representation, but I think it looks cool. And this is my talk, so I get to choose the images that I want. And also, it's actually the most accurate representation of the environment that's around these things. So what do we got in here? We've got our supermassive black hole down there in the center, and it's surrounded by that accretion disk that I keep talking about. So things orbiting around the black hole at very, very fast speeds, sometimes fractions of the speed of light itself. And when things are orbiting that fast, you have a lot of friction. Friction causes a lot of heat, and a lot of heat causes this gas to shine extremely, extremely brightly. AGN host galaxies, and then the older brothers of AGN host galaxies, quasars, are some of the brightest objects in the universe. And then as you get closer and closer into the black hole where the gravity is stronger, that means that you're making things move around faster, which means more friction, which means it gets even brighter. You've got stuff that's falling into the black hole, and you've got stuff that's falling towards the black hole and narrowly misses and then gets shot out as a jet that you see there too. But all these artistic representations are fun to look at, and they might look really cool, but I guarantee, or at least I hope, that you've seen a real image of a black hole like this. In fact, there is only one real image of a black hole that we've ever gotten. So hopefully, all of you remember one of the greatest recent astronomical achievements in history. This is the image of the actively accreting black hole that's at the center of the galaxy Messier 87. And this is the only real image of a black hole that we've ever gotten. And just from this image, we were able to measure the mass. The mass of this black hole is about 6 billion with a B. I don't know how well I'm coming out of your computer, but billion, 6 billion times the mass of the sun. For reference, that's 1,000 times more massive than the black hole that we have at the center of our galaxy. And the size of this thing, comparatively, the size of our black hole is about the size of Mercury's orbit. This thing is bigger than the orbit of Pluto. This thing is huge. And because I work with black holes like these, this is my research, the team, the Event Horizon Telescope collaboration, they actually gave me a sneak peek into a more enhanced version of this image. So I might get in trouble for revealing it, but if I were to just enhance this just a bit, you can see just a bit more detail. The folks over at Frankfurt in Germany actually made a simulation of what we're pretty sure the environment around this thing looks like. And so they ran the simulation to give us more insight into the behavior of stuff around it, and then kind of give some backstory as to why that image looks the way that it does. So here I'll play the simulation. And again, we've got that accretion disk, we've got stuff falling into that black hole in the center, and we've got stuff that's narrowly missing and getting slingshotted out as a jet. And so you see, if we change the orientation here, you can see some stuff falling in. You see that stuff that's closer to the black hole is brighter and it's warmer, much hotter. And if you orient it like this is kind of looking like the image that we saw with the jet almost coming towards us. And it's actually, this galaxy is actually emitting a jet that narrowly misses Earth. I mean, even if it was pointed directly at Earth, nothing would happen, but it just narrowly misses us. And so we know just from this stuff that the image that we got from the black hole, the accretion disk, the stuff around it that's falling in, is oriented like this. My hand's disappearing. Oriented like this, where stuff is orbiting this way, as opposed to it being oriented like this, where you would actually cut across the center of the black hole. The disk is oriented like this. Now, all this stuff is really cool, granted, which is why I study it, because it's endlessly cool to me. But why do I specifically look at these kinds of black holes? What is the big deal with black holes that are feeding on their environment? Well, the big deal is when we throw this stuff into simulations, meaning if we take all of the observations of the universe that we have today, and we combine them with all the laws of physics, and we throw them into a computer, a supercomputer, meant to simulate the evolution of the universe, what we're able to do, this is an example of one of those simulations, this is the folks over at Illustris. What we can do is make an educated guess as to what the early environment of the universe was, mainly the distribution of dark matter and the distribution of normal matter. And then we can just let it evolve with the laws of physics that we know. And if at the end of the simulation, when it hits present day, if it looks like what we see in the real universe, well, that must mean that we were probably kind of close with the way that the universe was back in the day. So we can use these simulations to figure out how the universe has evolved, what did it look like, what was the environment like? And that's what I want to show you here. So what this is going to show you is what we're pretty sure the distribution and density and all of the structure of dark matter was in the universe on the left. And then as we progress through time, in cosmic time, meaning chunks of the lifetime of the universe itself, we're going to see how normal matter on the right is affected. So it's going to show you how the temperature is changing over time. There is real matter there, but this is very early in the universe's timeline. The universe is 13.8 billion years old. And you can see on the bottom left corner here, we're about 500 million years after the Big Bang. So back in the day, the universe was very cold. So this is going to progress, and we're going to see how the dark matter evolves and how that affects the distribution of normal matter here on the right. So I'm going to play this now. And these cubes, these slabs on the side are 300 million light years in size. So this is a sizable chunk of the universe itself. So you've got this cosmic web of dark matter over here that's kind of condensing under its own gravity. And so on the right, remember, when you compress a gas, you're increasing the pressure and you're increasing the temperature. So blue is the coldest temperature, and then green, yellow, red, orange, those are increasing in temperature. And these are 300 million light years in size. So on the right, you're seeing galaxies and clusters of galaxies within these dark matter halo webs. And as things evolve, as they condense, you're not only making those galaxies interact with each other and collide and merge, but you are actively dumping a bunch of gas and dust and stars onto supermassive black holes that are there at the centers of those things, at the centers of clusters of galaxies, at the centers of galaxies themselves. And what you see happening on the right is these gigantic outbursts of energy of very high temperatures that are really large. One of those bubbles is millions of light years in size. So the effect of black holes feeding on their environment, the effect of as the universe evolved and more stuff was dumped onto these black holes, and as they grew and threw more of that energy back into their environment, the structure of the universe itself is drastically changing. You can see how much different the dark matter looks nowadays and how much different the structure of the normal matter looks like as we progress billions of years up till the present day. This is why it's important. This is why understanding active black holes is important, because we're pretty sure, based on the stuff that we know today, is that this is what they were doing back in the day. This is the hand that they had in forming and structuring the universe as we know it today. So the better that we understand active black holes today, the better we get an understanding as to what they were doing in the past, which means that we have a better understanding of how the universe was behaving and how it has evolved over its lifetime. So today, how do we study active black holes? What can we do? Well, just like before, we can measure the masses of these things. This is a really cool simulation from the folks over at Caltech. And so what we see again is a supermassive black hole at the center. We see an accretion disk around it, and we see those big thick clouds that I showed you in that cool image before. And what the illustrious simulation just showed us is that when black holes feed on their environment, they are very messy eaters. So what happens is that sometimes there's a flare that comes out of the disk, or some outburst of energy from stuff that barely fell into or barely missed the black hole as it was falling in. So what happens when that flare happens is that light gets emitted in all directions, just like a light bulb. A light bulb emits light in all directions. So some of that light comes directly towards us, and we can detect that. We get that signal. Some of the light gets shot out perpendicularly. And so some of it goes and then crashes into those really thick clouds, and those clouds reflect that light and directs it towards us, and then we get that signal. So we actually get two signals from this. We get an echo. We get a signal from the light that directly came towards us, and then a little time later, we get that second signal from the stuff that was reflected off of those clouds. That echo actually tells us the size of this thing. Because think about it, if the clouds were closer to the accretion disk, that means that the photons, that light that got shot out from the disk, didn't have to travel that far before crashing into those clouds and getting reflected. So the echo would be shorter, and we would know that the size of this thing would be smaller. And then reverse it. If the clouds were further away from the disk, that means that the photons had to spend more time before they crashed into those clouds. So the echo that we would get would take longer. We have to wait a little longer for that second signal. So we know that the size of that thing must have been bigger. If we combine that with how fast that we can measure those clouds to be rotating, then we can actually measure how much mass is in the center, or the mass of the supermassive black hole. And here's why. Think about the GIF of the solar system that I showed earlier. When things are more massive, things rotate faster, and the planets that are closer to the sun are the ones that rotate the fastest. So if I measure the size of these clouds, and then I measure the fact that they're not rotating very fast, well, that must mean that there must not be that much mass in the central supermassive black hole. But if I measured the same size clouds and they were rocketing around the black hole, that must mean that that black hole has to have a lot of mass packed into it in order to make things move as fast as we see them. So the size of this thing combined with how fast we can measure it to be rotating tells us the masses of these black holes. And this method, this technique, has a really cool name, and I'm only going to say it once, because once I say it, I'm not going to be able to say it again for the rest of the night. This method is called reverberation mapping. All right, that's one, that's it. I'm not saying it again for tonight. So what happens is, or what's happened after we started doing this for a bunch of galaxies, is that we took the masses that we've measured, and scientists also combined it with other properties of the galaxies around the black hole that we can measure. And we started seeing something like this. So what we're plotting here is the black hole masses that we've measured on the y-axis, and then we have how bright the bulges are, or how luminous the bulge luminosities on the x-axis on the left. And then on the other side, we have the amount of different speeds of the stars in those bulges that we've measured. And what we're seeing is that the black hole mass, for some reason, is correlated with these properties of their bulges, meaning that they influence each other. They have an effect on one another. Because for some reason, this graph is telling me that if I increase the luminosity of my bulge, so too will I increase the mass of my black hole. That if I know one, I know the other. If they weren't related to each other, if they didn't have an effect on one another, this thing would be a scatter plot. There would be no trend, there would be no pattern. But there is. If I know one, I can use this to know the other. That's crazy. And let me tell you why that's crazy. Remember the size scales here. We're saying that the black hole size compared to the size of the bulge is like a fly in a football stadium. So now what this is telling me is that not only is the fly aware that it's in a stadium, but the fly also somehow has influence over the number of people sitting in the stadium. You know, back when it was normal for us to sit in stadiums and watch a game. Anyway, The only way that that could be true, the only way that this could be real, is that black holes and the environments that they're around, their bulges, grow up together, they evolve together, or at some point their evolution was connected over cosmic time, chunks of the universe's lifetime. Well, if that's the case, then that's really interesting. Because if we look at these things and we see behavior of things that make up the universe over sizable chunks of the universe's timeline, billions of years, then that means that if we understand these things pretty well, then that actually helps us understand how the universe itself has evolved over billions of years. Okay, so what else do we got? We also got that the black hole mass, for some reason, is also connected to the total amount of mass, the total mass of stuff packed into the bulges that surround it. So, okay, here's where I come in. Here's where the stuff that I want to do comes in. Given all of this stuff and how black holes are somehow connected to the football stadiums around them, I want to know what else they're connected to. I want to know what else they influence. I want to see if there's stuff happening outside of the bulge. I want to see if black holes can influence things even outside of the stadium. Because if they do, then that'd be really cool. That'd be really interesting in terms of the implication of how the universe works. So what I want to do is I want to make a list. I want to make a list of things that I want to look at, and then I want to make a list of the stuff that I need in order to get to the things that I want at the end of the day. So given these relationships that I just showed you, I think that I might want to measure luminosity and I want to measure mass. For luminosity, I would need an image and I would need a distance for each galaxy that I look at, because the image will tell me how much light that the galaxy is producing. And then the distance will tell me how bright the thing actually is. Think about these in terms of light bulbs. If you're looking at a light bulb that's really close to you, you're pretty sure how bright the thing actually is. If you move the light bulb away from you, it will look dimmer. And if you move it even farther away, it would look even dimmer. If you didn't know the distance, if you didn't know how far away it was at all you could say is, I know how bright it looks to me, but I have no way of knowing how bright the thing actually is because I don't know how far away it is from me. And then for mass, the things that I would need are the rotation of every galaxy that I would want to look at, the size of each galaxy that I would want to look at, and the distance. Remember, I keep referring back to that solar system GIF. If I have more mass, I'm going to make things around it rotate faster. And I can always measure the size of things on the sky, but unless I know how far it is away from me, I don't know how big it actually is. So I have to know the distance. Well, immediately, what's popping out to me is that there's one thing that I need to measure right off the bat, and that is the distance to each galaxy. So how do we measure distance in astronomy? Well, what we do, if I look at a galaxy and I take an image with my telescope, assuming that it's just super easy to get time on the Hubble Space Telescope, what I get is the apparent brightness of that galaxy on Earth. Remember, this is a light bulb that's somewhere out in space. I can see the light that's coming from it, but I have no idea how far it is away from me. So I have no idea how bright it actually is. So here is the method that we use. We're going to measure the brightness on Earth. We're going to somehow find the true brightness of these things, the real brightness of these things. And the difference between those two numbers will tell me what the distance is. Because think about it, if those two numbers were the same, if the brightness that I see and the brightness that, I'm going to have to keep my fingers here, if the brightness that I actually see and the brightness that it truly is were the same number, that means that the object is right next to it. The further apart those two things are, the farther the galaxy must be, the farther the light bulb must be from me. We can always measure the brightness on Earth. We can always do that, unless there are clouds in the sky. So the thing that we need is somehow find the true brightness of these galaxies. Well, luckily, these are spiral galaxies, and spiral galaxies have a cool method called the Tully-Fisher Relation. And no, this isn't a real image of a galaxy rotating. It's just another cool thing that I found online. The name of the game here is that if a galaxy rotates faster, it's going to be brighter. Its true brightness is brighter. And that's what's shown on the right here. Another correlation where it's saying that if you measure the rotation of a galaxy, then the true brightness of the thing is correlated with how fast it's moving. So if I go and I measure a rotation of a galaxy, all I have to do is ask this thing what the corresponding true brightness is. Each of the rotation rate of each galaxy has its own unique true brightness. So, okay, I need to measure distance. I need to get its true brightness. And in order to get its true brightness, I need to measure the rotation of these galaxies. Simple enough. How do I measure rotation? How do I measure rotation of a galaxy? Well, the question that needs to be asked is, what do I want to use to measure rotation? For example, if I look at an optical image of a nearby galaxy, so if you flew right to this galaxy, this is the stuff that you would see with these things. And just for comparison's sake, this is what the same galaxy on the same scale looks like in the ultraviolet. Well, that's interesting. Already I see a difference in the structure, a very big difference. Remember, UV will tell you where the biggest, brightest, most energetic stars are being created. And remember where the star forming factories in the spiral are. They're in the spiral arms. So this thing must be making really bright, really big stars a lot because it's telling me where they're being made. It's tracing out all of those spiral arms. So if I'm trying to measure the rotation of the whole galaxy, I would probably want to use the UV over the optical because I see more of the galaxy in the UV. I see more structure there. And, you know, just for comparison's sake, if I were to look at this thing in the radio, the same galaxy on the same scale, this is what I would see. That's cool. And remember, radio traces out the cold stuff. So this is actually tracing out all of the hydrogen in the galaxy. Hydrogen is the most abundant element in the universe, which means that it's the most abundant element in spiral galaxies. And so this thing will reveal to me how big the thing actually is, because it's tracing all that cold, calm stuff. So I see most of spiral galaxies in the radio, because spiral galaxies have the most hydrogen. Hydrogen emits in the radio. All right, so I'm going to use this. I made my decision. I'm going to use this, and what I'm going to do is I'm going to measure the photons that are coming at me from hydrogen. I'm going to measure their flux, meaning all I'm going to do is count the number of photons that I detect at each speed, at each velocity that they're moving at. So remember, this galaxy is moving away from us with some speed with the expansion of the universe. So this thing is moving away from us with some speed. So if I ask how many photons am I counting, I'm going to count a lot of photons at one velocity, the velocity that this thing is moving away from me. But just like the Earth's rotation about its axis and our orbit around the sun, we are rotating, so too is this galaxy. This galaxy is rotating. So from my perspective, one side of the galaxy is always coming towards me. So how this works in terms of velocity is that the galaxy is moving away from me with some speed. And then from my perspective, one part of the galaxy is always coming towards me. So you have a receding galaxy and then a piece of the galaxy that looks like it's running away from me slightly slower, because it's moving away and moving towards me at the same time. And then the opposite effect happens on the other side. The other side looks like it's always moving away from me. So I have a galaxy that's receding and then part of the galaxy that's moving away. So it looks like it's running away from me slightly faster. So what's going to happen to my signal here is that some of the photons that I count are going to get pushed to higher velocities. And some of the photons that I count are going to get pushed to slower velocities. So this signal is actually going to split depending on how fast the galaxy is rotating. The faster the galaxy rotates, the farther away those two peaks are going to be from each other. Okay, so in real life, I'm going to target an AGN host galaxy, and I'm going to observe it with a radio telescope. Come on. Or not. There it goes. And, oops. My remote died. All right, I'm gonna observe it with a radio telescope. Get back on track here. This is the Green Bank Radio Telescope in West Virginia. And I have a lot of memories with this telescope. I observed 24 galaxies with this telescope. And you notice that telescope is observing during the day, during the night, when it's cloudy, when it's sunny. That's because radio, those energies are low enough to pass through all that stuff, which is why when you're in your car, you can hear a song playing on the radio, whether it's cloudy, sunny, night, day. So of the 250 some odd hours that I spent observing those 24 galaxies, I was observing during the night, during the day, during class. So the term sleep schedule is a bad word around me and my friends, so please don't say it to me, I'm going to start twitching. And then what we get in real life is a real hydrogen signal with those peaks that were split apart because of the rotation. So I did that for 24 galaxies. And so for my list here, I have the images and I have the distances, which means that I have all the keys that I need to measure luminosity. And I've also unlocked something else that's kind of cool. Let me show you. here's the stuff that I have. Here are my keys. If I have the luminosity of each galaxy, and I know how far away it is, which means that I know how bright it truly is, that actually means that I have counted up all of the stars in my galaxy. Think about it. Think about the light bulbs. If I have more light bulbs, that means that the luminosity is going to increase. And I know how far away it is from me, so I know how truly bright those light bulbs are. So if the luminosity increase, I have more light bulbs, so I have more stars. This thing counts the number of stars for me. And then with my Batman signal here, this is all from hydrogen. This signal is all from hydrogen. And again, if you combine that with the distance, this thing actually tells you how much gas is in your galaxy. That signal comes from photons that were shot out from gas. So if that signal is stronger, that means that there was more gas shooting photons at me. So that strength of that signal tells me how much gas I have in my galaxy, the total amount. If I add up those two things, I have the total amount of mass in what we call baryons, normal matter. The stuff that made up that 5% of the pie that I was talking about earlier with the universe, that's this stuff, stars and gas, regular normal matter. And so, okay, I have the total amount of normal matter in my galaxies, and I have their black hole masses. So now I'm able to ask the stuff that I wanted to ask in the first place is, are black holes, do they have influence on stuff that's outside of the stadium? Do black holes have an influence on the total amount of normal matter in their galaxies? And what we found is that it looks like that they do. Black holes do have an influence. Black holes do affect the total amount of normal matter in their galaxies. Now that's crazy, and the insanity is just going to increase from here. So fasten your seatbelts. To put it in perspective, what did we just measure? What we just measured is that all of the normal matter, all the directly detectable stuff, stars and gas. I got all that. But there's a ton of stuff that I haven't even touched yet. All of that dark matter, all of that missing mass, I still haven't touched yet. So now I want to ask, if I can somehow measure that, I want to see if black holes also have an influence on that stuff. So, okay, let's go back to my list. What do I need for mass? Well, I've already measured the distances. And to measure the distances, I had to measure rotation, so I got that too. So the only thing I have left to measure is the size of the sizes of these things. So how do I do that? I'll go over here. Here's another galaxy in my sample. This is NGC 4151, and here's an optical image of this guy on the right. And it looks like something happened to his ear. But the trick here is that we use hydrogen to measure rotation. And because that's the case, we don't want to look at the sizes that these things are in the optical. What we want to do is we want to measure the size of hydrogen. So we don't want to look in the optical. What we want to do is look at each of these galaxies and see how big they are in the radio. This is how it looks in the radio. So we want to measure those sizes. We use hydrogen for the rotation. We want to use hydrogen for the size. Compare apples and apples. And just as a fun little aside, the unofficial name for this galaxy is the Eye of Sauron. But okay, I've got all of my keys. So how do I actually measure the total galaxy mass? So here's my radio image. And remember that it's rotating. And if there's a point that I want to drive home tonight at all, it's that if something is rotating faster, there has to be more mass. If the sun had more mass, the planets would rotate faster. So the method for measuring the total amount of mass there is take the sizes of these galaxies, which I've got, take how fast they're rotating, which we've also measured, and that will tell us the total gravitational mass, or what's called the dynamical mass. So what I'm doing here is that I'm ignoring stars and gas. I've already measured those. And all I'm asking is how much mass needs to be here in order to make the galaxy rotate as fast as I'm observing it to be rotating. How much mass needs to be here to make the galaxy do what it's doing? And so we call that the dynamical mass. And so now I have those. I have dynamical mass. And now it's the constant question, do black holes have an influence on this mass as well? And the answer we found is it looks like they do. They have influence over this as well. This is starting to get insane. The size scales are getting crazy because here, this is what we just measured. What we did was we created a sphere around our galaxies, and that size of the sphere was determined by how big that hydrogen was. So that's the edge of the sphere. And then we just said, okay, here's a spherical bucket centered on that hydrogen. How much mass are we counting in this spherical bucket? So if you'll notice, the dynamical mass measures not only the normal matter, not only the baryonic matter there, but it's also measuring whatever dark matter was also captured in that spherical bucket that we put over that galaxy. So here's something cool. We can just, because we know what it is, we've already measured it, we can just take that normal matter away. And if we do that, then if we just subtract it all away from the mass that we just measured in that bucket, this actually tells us the stuff that's left over. The stuff that's left over is just the dark matter in that bucket, in that sphere. So now, again, I'm going to ask the question, do black holes have an influence on this mass as well? Lo and behold, you're just going to constantly see a pattern here. It does look like that black holes do have an influence on this stuff as well. The size scales are getting crazy. I'll put everything together at the end. But what's cool now is that we already measured the normal matter there in the center, and we measured the total amount of matter. So I can now say how much matter in that sphere is dark matter. What we're finding is that about 60% on average with the galaxies that I study is dark matter. So everything that you've interacted with is everything that you've seen in the sky is only roughly a third on average of the total amount of stuff that's associated with the galaxy within its disk, within that hydrogen stuff. All right, well, I'm almost done here, but my problem is that here's what we just measured. I'm still missing all that stuff outside. So I want to find some way that I want some way that I can measure just all of the mass that's associated with these galaxies. I want to find a way to measure all of it. In order to do that, I would have to know how big that dark matter halo was. And believe it or not, that's kind of the trickiest thing that I've talked about tonight. Because as soon as you go a little bit further from that hydrogen, nothing is emitting anything anymore. We can't directly detect anything after that point. So what do we do when we're stuck here? Well, we can make educated guesses. We can guesstimate based on simulations, the ones that I showed you earlier. When you're doing a simulation, you say, okay, here's where I think stuff is, here's where I think the dark matter is. And if I let it evolve and it reproduces what I see in real life, then that must mean I had a pretty good guess as to what was there in the first place. And so when you're doing that with a computer, you actually have to tell it where is the dark matter. And so you have a measurement of how big the dark matter is. Based on recent studies like that, what we estimate is that the size of the halo is about 10 times the size of anything that we can directly measure. So using that assumption, all we have to do is scale up the stuff that we've already measured and have a spherical bucket that's centered at the edge of all of that dark matter, the whole dark matter halo, and say, I want to add up all of the mass in here. And then finally ask the age-old question, are black holes connected? Do they have influence on the total amount of mass that's associated with the galaxies that they're in? And it looks like they do. And other studies are finding this as well. Okay, let me tell you how crazy this is. This is the amount of stuff that we just measured. So let's go back to that size scale stuff. We were saying that a fly in a football stadium is the size scale of a black hole in its spherical bulge. Then we went 10 times bigger than that stadium to get to the size of the disk. And then we went about 5 times as big as that to get to the size of hydrogen. And then what we just did is we went 10 times bigger than that to get to the size of the halo. So now we're saying that a fly flapping its wings in a football stadium has influence on something that's happening 500 times further than the stadium itself. That's insane. That's insane. Now I can do the same thing that I did before. I know how much normal matter is in there. All I have to do is take it away and say how much dark matter are in these galaxies on average. On average, the total amount of mass that's associated with a galaxy, 97% of it is dark matter. Everything that you've interacted with, everything that you've seen in the sky, everything that every telescope that we've ever created has detected has been 3% on average for the galaxies that I look at. That 24 galaxies, 97% of it is dark matter. Okay, I'm gonna wrap up here. Let's take a step back from this insanity. Let's connect this all together. This is another simulation from Illustris. And what I want to do is I want to zoom in on that dark matter cosmic web that I showed you before. This is the present day universe. And I want to zoom in and I want to change my filters and I want to see the different types of things that I can measure. So this is the gas temperature that I showed you before. And it's going to switch again to metallicity, meaning how many heavy elements has the universe created in its lifetime. All of this stuff that we can measure. You see all of this structure, you see all of this different stuff going on, the amount of things that we can measure. And if you go and zoom in far enough, you center on one individual galaxy. That individual galaxy throughout its lifetime and the galaxies around it, their interaction and the black holes that were actively feeding down in their centers are the things that played a huge role, had a huge influence on the structure of the universe around them. Look at all this. This is stellar light. This is the density of the gas, where blue is really highly dense and green is less dense. All this structure that you see, all the measurements that we can make, the structure and evolution of the universe itself has been dominated by the interaction of galaxies with their dark matter and the amount of energy that was poured back into the universe by galaxies that had a bunch of stuff that were dumped on them. These actively feeding black holes are things that had a huge influence on the universe as we know it today. So if we want to continue understanding how the universe works, why it looks the way that it does, how the structure has changed, what we want to do is study galaxies, dark matter, and supermassive black holes. And I think I'm finished blowing your mind for tonight. Hopefully I blew your mind a couple of times, but all I'll do now is say thank you, and I'll be more than happy to take any questions.
Fantastic. I wish we were all together so that you could hear the applause. I'm sure there would be a ton of it right now. Wonderful. So there are a couple of questions that have been posted in the chat. So I may go through a few of those just to begin with.
Sure.
And then if there are other questions, of course, please feel free to ask. So, but I'm just going to take my prerogative to say, first of all, thank you. That was fantastic. It did blow my mind several times.
Thank you so much. Thank you. I appreciate it.
Absolutely. So the first question from Eric is, galaxies accelerate away from one another. Do they accelerate at the same rate, or is the rate of the acceleration related to the mass of the black hole at the center of each galaxy?
That's a really, really good question. So as in the universe as a whole, the farther that you look, the rate of expansion, the rate at which galaxies are moving away from each other is the same. When you look at stuff that's nearby, you have gravitational interactions. So galaxies have a ton of mass associated with them. So the space between them with the expansion of the universe is increasing. But in the nearby universe, the force of gravity that galaxies have on each other is stronger than the rate of expansion itself. And so, for example, Andromeda and us are on a collision course with one another. So in about 5 billion years, we will collide. That it won't be that big of a deal because galaxies are so puffy and so the density is so low that we'll probably just pass right on through each other. But it's because we're so close to each other that the speed at which the gravity that we're inflicting on one another, it's causing us to move is faster than the rate of expansion itself. So in the nearby universe, no, the rate at which things are moving away is not constant. But the farther out that you look, the more constant things appear, because the farther you look, the faster the rate of expansion is. So as the rate of expansion increases, the gravitational interactions of things, the relative speeds of them kind of diminish because the rate of expansion gets so fast.
Okay, great. Lots of questions piling in here, and interspersed among many of the comments are applause, amazing talk, other things like that. So I just want to make sure you know that.
I appreciate that.
Absolutely. The second question from Renisha is, why are we assuming that the halo size can be 10 times the visible size in order to find the mass of the galaxy?
Ooh, that's a good question. Well, it's a guesstimation, right? So there's no direct way to measure how large the halo is. So in order to say we think that it's about here, we look at the same kinds of things that are going on in simulations, where we see a pocket of galaxies and we've let them evolve and they look like the galaxies that we observe in the normal universe. And so all we've asked is, okay, well, how big do those dark matter halos have to be in order for them to evolve and eventually look like the stuff that we see today? And for recent simulations, it's looking like, on average, again, each galaxy is not going to be exactly 10 times, but on average, it looks like the dark matter halo is roughly 10 times the size of anything that we can directly detect. That's why.
Okay, great.
I hope I answered that question.
I think that's a good answer. Another question here from Brian, who also says applause. Could you explain how you reconcile the 30% baryonic matter to 70% dark matter at the beginning of the talk with the 3 to 97% that you found for the galaxies you studied?
Absolutely, absolutely. So he's talking about here. Yeah, exactly. So the more that we've studied dark matter and their evolution with normal baryonic matter, we've found that the shapes of the halos themselves are not they're not donuts per se, like very symmetrical halos. What they look like are these cuspy profiles where there's a little bit of dark matter near the center of the total system, right? So you got your dark matter, and then at the very center, nestled in the center, you have your normal detectable matter. So what it's been looking like with the structures of these things is that there's a little bit of dark matter there, and then as you go out, the fraction of dark matter relative to normal matter increases exponentially. So it would make sense that if we move past the detectable radius of these things, then we're hitting the vast majority of where the dark matter is concentrated.
Great. Okay. Another question, why is there such a strong correlation between luminosity and rotation speed?
Between luminosity and rotation speed. Oh, for the Tully-Fisher relation. Got it. That is another great question here. Where did I put it? Here it is. The reason is because of the thing that I've been saying this whole time. If something's rotating faster, that means that it has more mass. So the underlying idea behind this is that if a galaxy is rotating faster, it has more stars. It's got more mass. And if you have more stars, the faster that you rotate, the stars are going to emit light. So the more mass and stars that you have, it directly translates to how much light that you're producing. So it becomes really useful for us when we're measuring distance, because the faster a galaxy rotates, the brighter that it's going to be, because you have more mass there to make it move faster.
Great. I'm just trying to keep track of all these questions. There's so many great ones. Let's see. Ram Prakash asks, would distance measurements be incorrect due to the path of light being curved due to the source's celestial body rotating, causing frame dragging and space being curved?
Whew. There's a lot in that question. Not for the stuff that we're looking at. It's not rotating that fast. Galaxies don't actually rotate that fast, so we don't have to worry about that stuff. And if it is a factor, it is extremely negligible given the uncertainties in the measurements that we make to get distance in the first place. If things were farther away, then you would worry about that. If there was something in the way, if there was a lot of mass in the way of something that we're trying to measure, then you would have to worry about the curvature of space itself. You would have to worry about lensing effects and stuff like that. So what we're looking at are nearby stuff that's not moving away very quickly, that's not rotating very quickly, that are in roughly isolated environments. So those factors are either they don't affect our measurements or they're negligible with their effect.
Okay. We got time for maybe one more. I'm trying to be mindful of the fact that this is a Zoom talk and it is Friday night, and I know that many people are on many Zoom talks these days, but there's so many great questions. I hate to not get to all of them. Kind of related to that last question, is gravitational lensing still used to image and measure galactic dark matter?
Yes, actually, yes. That's a great way to measure it, because the more that this isn't my area of expertise, but I have looked at some of those studies and have compared them to my results as well. If you have a lot of mass concentrated in a specific region, then, and if you're lucky enough to have something behind it, then you can see the lensing effect that happens. So the more mass you have, the more that it's going to warp the stuff. And if you model that, and if your models are accurate, that will tell you the total amount of mass that needs to be there to create the lens. And then you can kind of do what I did, was take away the normal stuff that you can detect. And that leaves you with the total amount of mass that you can't detect. That's the vast majority of why you're getting enough mass to make a lens in the first place. So yes, that is a great way that we've been able to measure dark matter masses, is with gravitational lensing.
I think many people on the call may be interested in this. Do you have any recommendations for a good book explaining this is from David, to amateur scientists? Fantastic talk.
Thank you very much. I know that Neil deGrasse Tyson has written a lot of stuff. I think it was Astronomy for Folks on the Rush or something like that, or for folks in a rush.
People in a hurry, or yeah, something like
people
that.
In a hurry, yeah. I think that, well, the first book that Stephen Hawking released, Brief History of Time, even his students had to say that no one's going to understand what the hell he just wrote, so he's going to have to simplify things. The sequel to that he released is called A Briefer History of Time, And it gets a little complicated, but I think it does a better job of explaining things in non-technical terms.
Great. Well, and the last comment I'm going to read is, well, two actually, that tie things up nicely. You deserve your own show. This is from Mandisa. You deserve your own show on Nova, Justin. You're such a brilliant and captivating presenter. And this was great, and great suit. So on that note, let's
Thank you so much. Thank you.
Let's all thank Justin for a truly amazing talk. Just really so much good information, so much cool data, and I know we're all going to be excited to see you wrap up your PhD and what amazing things come next. Hopefully that Nobel Prize.
I'm looking forward to wrapping up my PhD as well.
Now, I didn't mention this at the beginning, but yeah, lots of applause and thanks, bravissimo in the thread. I invite you, if you are not too tired out, to hang around just for another 10 or 15 minutes for a brief planetarium show. In normal times, of course, we would now have some cookies and coffee and then retire to the planetarium. But we do have the ability to do sort of a Zoom version of a planetarium show. So I invite you to hang around just a little bit longer. I'm like you, I know that it's late on a Friday night, and truly, we hit a record-breaking, I think 93 people were here tonight, which is absolutely fantastic. So well done, Justin, on drawing in a huge crowd. And I think everyone who was here was delighted, of course. So if you want to hang out, we'll go just for another 10 or 15 minutes. I won't keep you long, but I'm just going to switch over to sharing a screen. Let's see, have I forgotten anything, Professor Lovell, Amy Lovell? Do we, is there anything else that we need to announce before I move over to the not Delafield Planetarium?
Nope, I think you're doing great. Thanks so much, Justin. That was really, really, really educational talk and very engagingly presented. So thank you so much.
Thank you very much. Thank you. I appreciate that.
Absolutely. All right. So I'm going to go ahead and share my screen here. And oh, and someone in the chat says, since there's no cookies and tea, they're having a beer. That's good. I hope everyone goes and grabs a beer if you want one. That would be.
I approve. Way to go.
That's right, Justin. I think you have earned your beer. I think you can have that now. All right. So just give me thumbs up if you see the screen that we're looking at together here. Can you all see the same thing? Okay, great. This is some software that actually you can access on your own. It's called Stellarium Web. If you just Google Stellarium Web, you'll get the web-based version of the software. And it does sort of what we, try to do in the planetarium, which is, give you this kind of circular view of the night sky, right? And so you can look around the whole horizon to the east. You can zoom around to the north, right? There's someone's little house here. I'm not sure exactly where this horizon is. I think it's somewhere in Germany, I believe is where the software comes from. But so we're looking to the south here, and we have some things labeled. The green line is the meridian that runs from north to south. And then the red line is the ecliptic, which is usually we think of that as the plane of the solar system. And I want to just point out that the display is set so that you can see the Milky Way here, right? Justin did a lovely talk about galaxies. And of course, this is the galaxy that we're part of, right? This is our home galaxy. And then as you look, as you get away from the disk of the galaxy to this way to the west and the other way to the east, then we sort of see fewer and fewer stars. So in fact, if you did want to look at galaxies, right? If you wanted to find galaxies, oh, sorry, not trying to spin around quite that much, make everyone sick. If you did want to look at galaxies, you have a lot better time finding galaxies out of the plane of the Milky Way. You want to get out of this plane here because that's where all that gas and dust and star formation that Justin was talking about that happens in galaxies, that's all going along here. And if you want to see further and further out into intergalactic space, you want to look more away from that plane. A couple of other things that I just want to point out is that over here in the west is where the moon will get a new crescent moon in a few days. And if you click on the little time here, we can tick forward to the 15th. There we go. There comes the moon. So it looks like Monday night, we'll get a nice little crescent moon over in the west. And if you click on an object like this is just sort of a gee whiz thing about this software. You can track to that object, and then you can zoom in on it, and you can kind of get a telescopic view of the object, which is pretty slick. You can see what the face of the moon that you would see in a telescope if you had one out, and we're taking a look at that. Okay, so yeah, we want to zoom out a little bit. So coming back to our kind of view to the south, you know, and in the planetarium, when we can welcome you back to the Delafield Planetarium, when you sit in the planetarium, we generally set it up so that you're looking to the south. So this is kind of the view that you would have if you didn't crane your neck and sort of look back over your shoulder. You would see this part of the sky. There are a lot of things we can do in Stellarium that we can't do in the planetarium. So we'll try to take advantage of those kinds of things. For example, if you are interested in the planet Mars, you can go ahead and center on Mars, and we can do the same thing. We can do a nice little zoom in. Notice as we zoom in on things, right, these background stars, we just see fewer and fewer of them, but eventually we see the moons of Mars, and there we see, whoa, okay, I didn't even know we could actually crash on the surface if we want to. There is a lovely view of planet Mars. Okay, so if we go back, we can zoom out again. If you do play around with this on your own, if you use a trackpad, I'm just sort of brushing 2 fingers up on the trackpad, or if you have a scroll on your mouse, it's just using a little scroller on your mouse to zoom in and out. Another thing that's kind of fun to see here is we can look at something like the Pleiades. We can zoom in on that. The Pleiades is called an open cluster. And what's kind of cool about the Pleiades is that if we zoom in on it, we can actually see all of this kind of just dispersing gas, right, from this lovely cluster of high mass stars that's just formed. They're going to blow up as supernova before too much more time has passed, but they only live about 10 million years, right, these bluish stars, and they're just kind of diffusing those wisps of gas around them. And so again, what's kind of cool about this software is that when you get to a certain point zooming in on things, it actually goes to astronomical images of that source, right? And so it allows you to get a nice view of sort of our latest astronomical views of a particular source. All right, so that's the Pleiades. Those are high mass stars that are have dispersed the stuff around them. There's another high mass star that is part of a constellation that you're probably familiar with, and it's up at night, right? So we're in real time right now. So it's 9:09, right? And you may recognize this constellation here, which is Orion, right? The Orion constellation is sitting here right in the middle of the sky, middle of the southern sky at this time of night. And it has the very familiar belt and sword. And so if we click on one of these features, there's M42. Let's go ahead and track M42 and zoom in on that. And again, if we could have the Beck telescope, it might not look this good, honestly, depending on the night we have, but this is the kind of thing that we might look at this time of year, right? We might go ahead and give you a view of the trapezium stars in the Orion Nebula, which we can kind of zoom in on here. And compared to the Pleiades, this is quite a bit younger, right? These stars are very young and are just kind of blowing out. So you can kind of imagine you're sort of looking into a hot bowl of soup here, right? And the trapezium stars are sitting in the middle of that hot bowl. And this stuff is sort of this gas, this hydrogen gas, right? Justin talked about hydrogen gas. This hydrogen gas is sort of getting bubbled out of that bowl towards us. And that's why it's so bright in the sky. I haven't played around with this enough to know if you can look at other frequencies or wavelengths, but you know, it would be nice to zoom in on, for example, M42 and take a look at the radio image, right? Justin did a very nice job about talking about all the different wavelengths that we see in the night sky. And those different wavelengths tell us different things, right? And so there are ways in which we can see the hot gas, and oh good, Justin's got a beer. There are ways in which, we can see the stars, or we can see the hot gas, or we can see the dust, right, in the infrared or radio or optical. So all these tools and instruments we have give us different views of the same object that help us come to a deeper understanding. So I promised I would keep you about 15 more minutes. And so the last thing I'll show you is just kind of moving ahead over the next few days. So this is Monday, Tuesday, Wednesday, is that right? Yeah. So Thursday of next week, notice the moon and Mars are going to be close to each other in the sky. So you should see that nice kind of waxing crescent moon, very close to a bright object that'll of course just look like a star. It'll look like a very bright star, but it should be very close to the moon, and Mars will be close to one another, and the Pleiades, right? So we'll have a nice little grouping. In fact, the next day, the moon then goes tearing past, right? And so what you'll notice is that the moon does two things as it's moving across the sky. Its phase is changing, right? It's moving towards that first quarter moon. By the time it's past the meridian, it's waxing gibbous phase, right? But the moon is moving about 15 degrees per day across the sky, right? And so if you sort of know where the moon is one night at a certain time, right? Because we're kind of jumping ahead a day at a time, right? A day at a time at the same time of night. This is all at about 9, 10 in the evening. So if you go out over the coming week, you should see the moon moving across that sort of west to south part of the sky. And it'll move past Uranus, which you won't see without a telescope. It'll move past Mars and the Pleiades, which you will see without a telescope. And then it'll move past this bright star Betelgeuse, which is in that lovely constellation Orion. So something to look for in the coming week. And I don't know if any of you watched The Expanse, but now Uranus is scarier to me because there's a large ring out there past the orbit of Uranus. If you don't watch The Expanse, you won't know what I'm referring to, but it's terrifying. So I don't know what it is yet. Don't tell me. I'm only in season 3. Okay, so all right. Well, we are at the end of our time. It's almost 9:15. I just want to say thank you so much for being here. I truly love that a big group of people comes out on a Friday night. We're all so zoomed out, but thank you for sticking with us through these hard times. And we're trying to stick with you and bring you fun things. And gosh, we couldn't have asked for a better speaker than Justin. So let's give him another round of virtual applause. Thank you so much. And I hope that you all are safe and well, and I look forward to seeing you for our concert next month. Thanks, everybody.